Okay, let us see the effect of poles and zeros on the frequency response of a given system. For that purpose, let us quickly review the axis relation between the analog frequency f and the digital frequency capital omega, which is called normalized frequency radians per sample. As already we have discussed earlier, this is the relation capital omega is equal to small omega into sampling time ts. Small omega is the frequency related to the analog signal. So that is equal to twice by f by fs. Now you see, when f ranges up to fs, capital omega ranges up to twice by. So fs point in f is equivalent to twice by point in capital omega. Here it is 0 to fs is 0 to twice pi. Now you see, when a signal is sampled, the frequency response is repeated with the repetition rate fs, and to avoid the aliasing, normally we restrict the frequency response from 0 to fs by 2, that is the Nyquist frequency. So normally we plot the frequency response from 0 to fs by 2, because the other part fs by 2 to fs will be the mirror image of the part from 0 to fs by 2. So our range of interest is 0 to fs by 2. Similarly, here the range of interest for capital omega will be equivalently 0 to pi. Now whenever the axis is drawn like this, that capital omega within bracket in has to be multiplied by pi radians per sample to convert to here. That means we normalize this range 0 to pi such that the range becomes 0 to 1. This is called normalization. Range is restricted to 1. So our range of interest is restricted to 1 here. That means this is the normalized frequency range. So we can convert this to this by multiplying by pi. So just notice that the frequency in hertz, whenever it ranges from 0 to fs by 2, equivalent here is 0 to pi, equivalent here is 0 to 1. Now let us go to the filter design analysis tool available in MATLAB, whereby we can see the effect of pole zero positioning to the frequency response of a system. For that purpose, let us take an example system, a low pass Butterworth second order filter sampled at 40 kilohertz rate. Let us put anything for the cutoff frequency. Let us design the filter. So point to notice is the sampling frequency is 40 kilohertz. So we expect that the frequency response will be from 0 to 20 kilohertz, that is fs by 2. Here you see the range ranges from 0 to 20 kilohertz. Okay. Now whenever you make it normalized frequency, it is 0 to 1. Okay, has to be multiplied by pi. If you multiply this one by pi, so range will be 0 to pi, as already we have seen. Okay, so let us keep it on frequency. Now quickly check the impulse response, that yes, the impulse response is converging. That means the system is stable. Now let us go for the pole zero plot. So here you see the pole zero position in the z domain. The crosses represent the pole positions, the circles represent the zero positions. Okay, as because this is a second order system, we have got two poles. Okay, now forget about this part right now. Let us quickly again review here the scale relation here. Here when you move in this direction from 0 onwards, that means you are changing the frequency omega. Similarly here also, that is equivalent to saying that you move through this unit circle starting from here. This is the 0 position, frequency capital omega. This is the 0 position. So when you move through this, that is pi by 2, and when you move up to this is pi. So capital omega 0, pi by 2, pi, and equivalent frequency in hertz is 0. Here it is 10 kilohertz, here it is 20 kilohertz for this. Okay. So now let us see the effect. Now when we put the 0 here at the center position, that means the distance from all the frequencies when you move through this unit circle is same from the 0. So effect of 0 to all the frequencies will be same. That means we are nullifying the effect of 0 on any particular frequency. Okay, such that we can see the effect of poles specifically. Now again I am restating, whenever you move through this unit circle, that means you are moving through the j omega axis in S domain, equivalent movement there. So whenever you move through the j omega axis in S domain, that means you are explicitly changing the frequency only. So here also the equivalent movement is through this unit circle starting from here to here. Okay. So when you move through this, that means we are changing the frequency. Okay. Now you see, let us position this pole near to the 0 frequency. This position is 0 frequency. So we are putting the pole near to 0 frequency, near compared to other frequencies. So 0 frequency, this distance is smaller compared to every other frequencies. From this frequency, what is the distance? This much is the distance. So that is further. So it is nearer or nearest to the 0 frequency. You see the effect in the frequency domain, you get amplification at 0 frequency. Okay. So the pole you put at a particular position, that particular position you will get maximum here, I mean amplification. Let us put the pole here nearer to this frequency. What is this frequency? This frequency is 5 kilohertz here. This is 0, this is 10 kilohertz, this is 20 kilohertz for this range. So this position is 5 kilohertz. So we are putting a pole near to 5 kilohertz. So we expect a peak at, this is 5 kilohertz, this one, yeah. So we expect a maximum or amplification at 5 kilohertz. What we get here at 5 kilohertz maximum. So when you put it near to 10 kilohertz, we get maximum at 10 kilohertz. So that way, this is the effect of pole. You get maximum to that particular frequency, you put a pole near to. So now you see, keeping the frequency fixed, and now as you move further from the unit circle, the amplification reduces. As you move nearer to the unit circle, amplification increases at that particular frequency. Here frequency is fixed 10 kilohertz. But as you move outward further, the amplification decreases. As you move closer, the amplification increases. So this is the effect. Similarly here, for the zeros, the same effect is observable. Let us put the poles at the center position. such that the effect of pole at a particular frequency is nullified. Effect of pole for all the frequencies are same, because whenever you put a pole at the center position, the distance from that pole to every frequency when you move through this unit circle is same. So effect for the pole for all the frequencies will be same. So now let us see the effect of 0. So similarly, as already told for the case of pole, here you see when you put 0 near to 0 frequency, you get minimum, I mean maximum attenuation at 0. Similarly, when you put the 0 near to 5 kilohertz, you get maximum attenuation at 5 kilohertz, near to 5 kilohertz. When you put the 0 near to 10 kilohertz, you get maximum attenuation at 10 kilohertz. So you see the similar effect. For the poles it was the amplification, for the 0 it is the attenuation. So you put near to that particular frequency, you get the effect in the frequency response to that particular frequency. Now, as already told for the case of pole, here also as you move the 0 nearer or further from the unit circle, the effect changes. What is the effect? As you move closer to the unit circle, attenuation increases, amount of attenuation increases. As you move further, amount of attenuation decreases. For the pole it was the opposite. Okay, for the pole, as you move closer to the unit circle, the amplification increases. Okay, but for the zeros, attenuation increases. So effect increases as you move closer to the unit circle. Effect for the 0, effect is attenuation. For the pole, effect is amplification. Okay. Now you see, by positioning this pole and 0, we can get the desired frequency response here. As you see here, it looks like a band reject filter. We can convert it to band pass filter. How? Let us see, at 10 kilohertz we want the pass band from 8 to 12 centering around 10 kilohertz. So what you can do, we can put a pole immediately at 10 kilohertz. Okay, we can put a pole at 10 kilohertz. So there will be amplification at 10 kilohertz, but we'll have to shape it. We'll have to get attenuation in this side also, right side. Left side already attenuation is there. Why? Because already we have put some zeros near to 0. So right side attenuation is there. Yeah, left side. So let us put the right side, I mean around 20 kilohertz. From 14 to 20 kilohertz we want some attenuation. So we can take zeros from here, we can put at the similar position as it is to make it a balanced one. Okay, so we can delete this, so it's a balanced one. So you see a band pass sort of frequency response we get. We can make this band flatter by putting some poles around 10 kilohertz from 8 to 12, such that here the amplification increases, here also the amplification increases. So we can take some pole from here and we can put some pole here and here. You see, it become flatter. More pole you can take, it will be more flatter. Okay, and you need to arrange it symmetrically such that you get the desired response. Okay, so you get a band pass filter, quite okay it is, from 8 to 12 the cutoff frequency we can say. Okay, so let us quickly check whether the system is stable or not. You see the system is stable. You can verify any of the poles, take any of the poles outside, put outside, you see the system become unstable because the impulse response increases. So system is unstable. Any pole, any of the pole, if you take any of the poles and put it outside, the system will be unstable. So that is also verified. Okay. This is the magnitude response. Okay. So let us stop here today. We will have more videos later.